Welcome to everything you ever wanted to know about position time graphs and velocity time graphs. I will be your guide, Mr. Jeffrey Bosdet. Here we go. If you've got a position time graph, like say this one, like in your practice test, and I say, what is the displacement at 20 seconds? Displacement is just how far you are from where you started. You started at 0 here, and at 20 seconds, your position is at 40. You are 40 meters from where you started in the positive direction, whatever that may be, whatever you have decided is positive. How about velocity? We've got a position time graph, so anytime you're kind of change in y divided by change in x is something, like position or distance divided by time is velocity. Therefore, slope of our graph is going to be velocity. So in this case, at 45 seconds, that falls along this line. I don't really care where, because the whole line has the same slope, same tiltiness. So all I'm going to do is figure out rise and run. It looks like my run is 15 seconds from 40 to 55, and my rise is 40 meters. So if I went, so my slope, I'm going to say my velocity is equal to my slope, which is my rise over run. So it's going to be 40 divided by 15, which I believe is 2.6 repeater meters per second. That's all you got to do there. Again, velocity at 30. 30 lies along this line right here. I don't really care where, because it's same tiltiness everywhere, same velocity the whole time. So I'm just going to use the whole bloody line to figure out what the slope is, because the velocity of a position time graph is the slope. And in this case, it looks like my rise is actually a fall. If it goes from 60 to negative 40, it looks like it is dropped by 100. And it took, we went from 15 to 40 seconds, so that looks like 25 seconds. So my slope looks like negative 100 divided by 25. I have a velocity at 30 seconds, and 25 seconds, and 22.37 seconds. At everywhere along this line, I have a velocity of a negative 4 meters per second. Or at least 4 meters per second in whatever direction I've decided is negative. And that's how we do this little bit. A couple other little things, displacement versus distance. If I want to find displacement at 40 seconds, that is not too hard, like we said before. I started here, and now I'm at position negative 40. So my displacement is 40 meters in whatever direction is negative. And my average velocity is always, so this is a great formula, it's always equal to displacement over time. And in this case, in the first 40 seconds, I have gone a negative 40 meters total from where I started, and it took me 40 seconds. So on average, my velocity was negative 1 meter per second. Yeah, at no point is my velocity actually negative 1 meters per second. Well, yeah, no, it isn't. 0 here, it's 6 meters per second here, and it's minus 4 meters per second here, but on average is minus 1 meter per second. Now, what's the difference between displacement and distance? Well, with distance, we don't care about which direction we're going. So the fact that we went 60 meters in the positive direction, and then another 60 meters in the negative direction, and then another 40 meters in the negative direction, we're just going to count it all as like distance run or whatever. So I went 60 meters in the positive direction, and then looks like I went 100 meters in the negative direction from there. From 60 to negative 40 is 100. So if I add this up, we got our 60, and then we got our 100. I went 160 meters in the 40 seconds. That's what I record if I'm doing my run. Now, average speed is nice and easy. It's the same formula as average velocity and looks exactly the same, except instead of average velocity, this is average speed, and instead of distance up top, instead of displacement up top, it's distance. So the only difference in this case is we will put 160 meters in for our distance, and our time is still the same. It still took 40 seconds. And notice a very different value. We were going on average 4 meters per second the whole time. And that's it for position. Moving on to velocity time graphs. First thing with the velocity time graph, if you want to find the velocity, just read the graph. So right here at 20 seconds, notice the velocity is 40 meters per second. And if we want the velocity at 35 seconds, right here, notice it is -20 or 20 meters per second in the negative direction. If we want acceleration, one thing that should be burnt into your brains is change in velocity over time is acceleration. That's the definition. That's how quickly your velocity is changing. Anytime your y variable divided by your x variable is something useful, the slope is that thing. So we're just trying to find slope. Slope of a velocity time graph is acceleration. So at 7 seconds, that puts us along this line. I don't really care where because it's the same slope the whole time, so I can use the whole line to solve for slope. So I'll just say, hey, A equals slope, which is our rise, which looks like 60, divided by our run, which is 10. So if we do 60 divided by 10, a rise or a run, we get 6 meters per second squared in the positive direction. At 22 seconds, that puts us along this line right here. Again, acceleration is the slope. It's the change in velocity divided by change in time. It's the rate of change in velocity. So that's what we're looking for. So again, A is the slope, and we'll just use our other line. It looks like our rise for that one is -100. And our run from 15 to 40 is 25. So if we've got -100 over 25, during this section here, if we've got a velocity time graph, we have an acceleration of -4 meters per second squared. So that's the basics. The tricky ones with velocity time graphs are displacement. Because anytime your y variable times your x variable, or your average y times your x, is something useful, the area under the graph, or the area between the graph and the x-axis, is that thing. So in this case, we want to find, if we want the total displacement over the 55 seconds, we need to find all of these areas. So we've got a triangle, a rectangle, a triangle, another triangle, and a triangle. I'm just going to do this really fast. Triangles are base times height divided by 2. So 10 times 60 is 600, divided by 2 is 300. So this little area has, or this little triangle has an area of 300, and therefore a displacement of 300 happened there. Here, rectangles are just base times height, so it's going, got a base of 5 and a height of 60, which is again 5 times 60 is 300. And then this section here, base times height divided by 2, we've got a height of 60, a base of 15. 60 times 15 divided by 2 is 450. Right here, we've got a height of -40 and a base of 10. So this will have an area here of 40 times 10 divided by 2, which would be 200, or -200 rather. And right here, we've got a height of -40, a base of 15. So 40 times 15 divided by 2 is the same as 20 times 15, which is negative 300. So our total displacement is all of these suckers added up, where 300 plus 300 is 600, plus 450 is 1050, and it looks like we're going to minus 500 here. So it looks like our total displacement is 550 meters. That was from 300 plus 300 plus 450 plus negative 200 plus negative 300 gave us this. But now that we've got our total displacement, we know that our one formula that always works for average velocity, if acceleration is changing, which it certainly is, we've got 6 to 0 to negative 4 to whatever the heck that is, I forget. But this formula will always work, and we know our total displacement is 550. And our total time is 55, which means our average velocity is just 10 meters per second, which works out very nicely. And if we were asking distance and speed instead of displacement and velocity, it's exactly the same, except we don't make these negative. We went 1,050 meters here, and then we went 500 meters back the other way. For distance, we're recording run distance. So like you don't start subtracting from your run distance if you turn around and go the other way. You just add the absolute value kind of. So we have 1,050, or maybe I'll just add them all up in this case. So it'd be 300 plus 300 plus 450, 50 plus 200, we're making it positive this time, plus 300, which we're also making positive, which should give us a total of 1,550, I believe, meters is our total run distance or whatever. Then if we want average speed, again, the same formula, but now we're talking speed here and distance here. And so it'd be 1,550 divided by 55, and whatever the heck that is, that would be 20 something or other, 20 something. I'll let you do the math. This has been how to do pretty much any type of graph question I'd possibly ask you. Make sure you can do it all before the test, please. This should be not the hardest marks if you know how to do every one of these tricks, because they're the only types of things I can ask you. Thanks for listening. Good luck.